stop.
The lift of a wing is a function of the angle of attack. When the angle of attack increases, there is a progressive separation of the airflow from the upper surface of the wing. The lift reaches its maximum and then decreases more or less abruptly. This is the stall. For the development of new airplanes, aerodynamicists need to visualize the airflow on the wing. This is done using small plastic cones, called tufts, attached to the wing with a short string and Scotch tape. The tufts allow the visualization of where and when the airflow starts to become disorganized when approaching the stall. It may help in the definition of improvements. Strakes are installed on the engine nacelles. At high angle of attack, a vortex is attached to these strakes. It gives energy to the airflow to delay the separation on the wing. The measurement of the stall speeds of an airplane is essential because in all circumstances, the crew must maintain a sufficient margin above this speed, even for an aircraft equipped with low-speed protections. Stalls are performed in direct flight control law, which means that the deflections of the control surfaces are proportional to the deflection of the side stick. On a specific display, the pilots monitor the key test parameters obtained from the flight test installation, angle of attack, and side slip. The stall test starts with the airplane stabilized and trimmed at a speed about 25% above the estimated stall speed, with the thrust levers at idle. Then the pilot pulls back slowly on the stick. The angle of attack increases progressively and the speed decreases. When approaching the stall, there are audio and visual warnings.
Stall, stall. Stall, stall.
During flight tests, the audio warning is cancelled by the other pilot to facilitate verbal communication between the crew. One crew member announces the angle of attack values. The flight test engineers visualize on their screens the increase of the computed lift coefficient with the angle of attack. When it reaches its maximum, they call brake.
Brake.
This is the stall. The pilot then recovers. Depending on aircraft type and configuration, some lateral motions or pitch down may occur, such that the pilot must recover before the announcement by the engineers.
Stall, stall.
For recovery, the pilot pushes the stick forward to decrease the angle of attack immediately. As the speed increases, he gently adds some thrust to avoid losing too much altitude. When the speed is sufficient, he pulls back smoothly on the stick. The stall maneuver needs to be flown very precisely. Roll control is achieved without spoiler deflection before the stall because it decreases the lift. Pitch control must be very smooth up to the stall with a permanent backward displacement to increase the angle of attack. Any stick release leads to a significant lift decrease and may not allow a precise curve of lift versus angle of attack to be established. On transport aircraft equipped with slats, when they are deflected, the angle of attack for the stall is usually between 17 and 20 degrees. Some buffeting appears before stall, linked to the separation of the airflow from the upper surface of the wing. On an aircraft in clean configuration, the buffeting increases progressively up to becoming deterrent. To avoid any subjective interpretation, the limit is determined by analysis of the variation of the vertical acceleration at the pilot seat. There is no loss of control, and it is not a limit for the lift increase, but for certification, it is considered as the stall. In some aircraft configurations, when approaching the stall, there may be a pitch-up motion. The angle of attack increases without any action from the pilot. Therefore, the crew needs to smoothly control this pitch-up to maintain a progressive increase of the angle of attack. When the angle of attack is close to the stall value, there are frequently high loads on the horizontal tailplane due to the buffeting. The flight test engineers monitor these loads. During the development of a new aircraft, at the very beginning of the test period, stall tests are devoted to the optimization of the various aerodynamic configurations. The main target is the reduction of the stall speeds. In many cases, it allows takeoff and landing distances for a given weight to be decreased. Improved performances also reduce the noise footprint. Adjustment of slats and flaps deflection and size and position of the strakes on the engine nacelle are some of the possible ways to optimize stall speeds. Later on, more stalls are performed for several reasons. First, the stall speeds are used to compute the aircraft performances. For each configuration and for several weights, 3 successful tests are carried out to obtain a very precise speed value. In addition, the stall characteristics and also the angle of attack and elevator deflection associated to the lift coefficient need to be identified for the fine-tuning of the stall protection of the flight controls in all configurations. During the flight test campaign of a new airplane model, around 1,000 stalls are performed.